Okay, well here we go. Welcome the universe to 11 triple. This is the first booklet of 3. So let's give this a go. What is the universe? Well, if we have a look at these individual pictures, what is it? It's space. Well, it's space, time, matter, and energy. 1, 2, 3, 4. The universe is everything. Well, how big is it? Well, think about a length of string. How long is a length of string? It would appear that the furthest object away from us that's ever been measured is this little creature here. It's a gamma ray burst of energy, and it has been measured at approximately 13.14 billion light years away. So the universe is 13.7 billion years old, approximately. So the edge of the universe is only 0.6 billion light years further away than RGB, etc., etc., etc. So if we have a look at the diagram here for a second, if that is the beginning of the universe here, and GRB, etc., etc., is over here, then the edge of the universe is only another 4% further on. You can think of the universe as a sphere, and it would be approximately 28 billion light years in diameter. In other words, approximately 28 billion LY light years across. But what is beyond it, out here, or over here, or even over here, no one knows at present. This picture here was taken in 2004. Just have a read through the rest of this paragraph, if you would. You can see hundreds, if not thousands, of stars and galaxies. In fact, it would appear that what was thought to be a blank patch of sky, having exposed the camera for long enough to take in the light from what was in actual fact there, it would appear that there was 10,000 galaxies in that allegedly blank space, each containing over 100 billion stars. The size of space surveyed in this picture is also fantastic. Imagine looking at space through a 2.5 metre long drinking straw. That's the size of the patch of space that is in this photo. Many of these galaxies are so far away from us that the light reaching us from these takes billions of years to arrive. Even though light is travelling at 300,000 kilometres a second, the light takes billions of years to reach us. So, we're going to look at two sets of data gathered by astronomers. The first data set was used by a famous American astronomer, Edwin Hubble, in 1929, and data set 2 is a collection of modern data using observations and measurements of distant exploding stars. This is data set number 1, Edwin Hubble's 1929 data set. And the variables that we're looking at are the distance the galaxy is to the Earth in light years, and the speed it is moving away from us, its velocity in kilometers per second. So it would appear straight away from this data set that as the distance the galaxy from Earth increases, so does its speed away from us. I'm going to say that again. The more distant the galaxy is, the faster it's moving away from us. Okay? Now you are asked to plot this on some graph paper. And what you should find is a diagram that looks a little bit like this. Distances along the bottom, velocity up here, like so. And when you plot the points, they are quite random. I want you to do this graph, and you could put in a number of lines of best fit. I mean, you can tell, if I was to draw in a line of best fit, if you go through the origin, you know, it could go up like that, and that goes with our trend. As the distance increases from the galaxy to Earth, then the velocity increases as well. But you could put in numerous lines of best fit in here. It's not supremely good data. Okay, the plots are not close together at all. What did Hubble conclude? Okay, Hubble concluded the further away the star was, the faster it was moving. In other words, what he's saying is the universe is expanding. And he actually came up with a mathematical got it, relationship between the velocity and the distance. If you double the distance, then you double the velocity. And this became known as the Hubble Constant, HO. Now this equation will always be given to you in the exam, but I would like you to know the units. Velocity, V, is in kilometers per second. The distance is in megaparsecs, okay? Big M, PC. More about that in a second. And the Hubble constant is kilometers per second per megaparsec. Now, a parsec, or PC, is a measurement of distance. We'll be coming back to this in double a little bit later on. It equals 3.26 light years. It's used to describe the largest structures in the universe, such as galaxies, when units of light years are even considered too small. Why don't you have a go at working out the number of meters in 1 parsec? Now, to do that, it is 3.26 light years in 1 parsec. Now, a light year is the amount of meters light travels in a year. So we've got to multiply that, a light year, by 3.26 to get the parsec. So light travels 300 million meters per second. Now we've got to work out how many seconds in a year. Well, in a minute, there's going to be another 60. In an hour, another 60. In a day, there's 24 hours. And in a year, there's normally 365 days. If you were to multiply all those numbers together, you would get the number of meters travelled in 1 parsec. That is going to be quite a big number. Now, scientists like looking at what other scientists have been doing, and almost as soon as Hubble published his data, other astronomers realised that if the universe was expanding, there must have been a time when the universe was much, much smaller. They're just going back in time. In fact, the universe must have started in one place at one time in the past. In other words, there must have been a fantastic explosion, i.e. the creation of the universe. This became known as the Big Bang. So Hubble, although I don't think he coined that term, had actually discovered this theory about the creation of the universe, which we now know as the Big Bang. Now, this modern set of data provides us with a much clearer idea of what is going on. And I'd like you to plot that data on a graph, and what you should get is a much cleaner line like so. I'm trying to put the axes in. Distance again in parsecs, a velocity in kilometers per second, and you will find that you are getting a much tighter set of data which you could put a line of best fit through. And you can also calculate this Hubble constant if you are able to extract data from a line graph. We're trying to find out the gradient of this line graph. Take a line straight across, take a line straight down. You've got two sets of data, one for velocity, one for distance. You can work out the Hubble constant, which is exactly what we are going to do in a moment. This value here is 25,000 kilometers a second. This value here is 350, boom, megaparsecs. We'll be using that in a second to work out the Hubble constant. That will be question 12. So I'd like you to have a go at question 5, question 6, question 7. Question 8, can you draw any other lines showing patterns in the data? No, because of course all the plots are tightly packed together on this line of best fit. So we now, I don't know why, but we jump to question 12. Calculate the gradient. In other words, calculate the Hubble constant using this equation. HO, Hubble constant, will equal the velocity divided by the distance, 25,000. That's an example that I picked out, but you could take any extraction lines from that line of best fit that we've just done, divide that by its relative distance in megaparsecs, 350, and that gives us a Hubble constant of 71.43 kilometers per second per megaparsec. Don't worry about these units too much, right? Astronomers now have many more points plotted on this graph using very accurate and powerful telescopes. They've worked out that the Hubble constant has a value of 67.8 megaparsecs, plus or minus 9. So this value here is not a bad effort, to be honest. And this gives us the age of the universe as about 13.8 billion light years old. There's a margin for error. It's plus or minus 0.12 billion light years. So the edge of the universe could be 13.82 billion light years away from us in all directions. Now, question 10. Why are modern astronomers very confident about Hubble's law? Pretty simple, really. You've been given the answer here. They've got a lot more data, a lot more readings that have been reproduced using very accurate and powerful telescopes, and they're all very close to this line of best fit. And then question 11. If the universe is da-da-da-da, 13.82 billion years old, what are we trying to work out? How fast will the furthest objects be moving away from us? Well, you'll be given that equation again. Velocity is the Hubble constant multiplied by the distance. You'll be given that. and the Hubble constant is 67.8 multiplied by the distance travelled, which is here, 4319 megaparsecs. You multiply those two together and you get 292,828.2 kilometers per second. That is very, very close to the actual speed of light, which is approximately 300,000 kilometers per second. So how fast are the furthest objects in the universe moving away from us? They're moving away from us, apparently, at that figure. These are galaxies moving away from us at this speed, which is very, very close to the speed of light. This indicates that the universe is expanding rapidly. And if you think about it, if you go back in reverse, the opposite to expansion is contraction. And at some stage, billions of years ago, about 13.8 billion years ago, there must have been a single point, a singularity, where everything was squashed in to an object the size far smaller than the grain of sand. And then it's exploded outwards for whatever reason, and this whole thing is called the Big Bang Theory.